Hello, it's Patrick McGrorty again. I'm here to do my first validation video for the final here. So we'll get into sharing for you. All right, show this guy. You wanted to start with item 3 in part 1. Should be right about here. We're looking at this graph of g of x here, and we're looking for first part as x approaches negative infinity. Over here, we're looking at it converging below. It's bumping up against and never quite hits 1 or -1 here. So as this graph continues onward towards negative infinity, as the number grows, value of x grows infinitely smaller. The graph converges on 1 but never quite touches. So that'll be our horizontal asymptote for x as it approaches negative infinity. As we're looking at the opposite direction, as x grows very large, we're looking at the graph here oscillating back and forth above and below, but as you can see, the oscillations are getting smaller and smaller, which means it will eventually converge um, as it grows much larger to the value of 2 right here. So as we go further on, it should straighten out as the oscillations get infinitely smaller and converge on 2. Um, admittedly, I'm not quite sure if we can count that as an asymptote because there's nothing that's saying that it can't necessarily be 2 at any point because it is crossing one way or the other. Um, so, I mean, technically it could probably land on 2, but for the purpose of this, as we're looking for asymptotes, I went ahead and gave it the value of 2 here. So, moving on to 5 here. So, both of these graphs do have discontinuities, excuse me, at 0, where this guy disappears down here. So it will never actually touch 0. So the graph is not continuous across the y-axis. Same goes for f of x here. We look up, we can see the graph physically stopping short of crossing the y-axis and then starting again on the other side. So the graph doesn't continue across this y-axis here, so there's a discontinuity there as well. So discontinuity there because analytically the limit of the function as x approaches these values are not equal to the value of the function at these input values of x. So if we're inputting 0 for either one, for this function or this function here, we're not going to get a value equal so to what x approaches as it comes to this y-axis here. Okay, so that's pretty much that for that. We'll move on to number 8 here. Okay, when using direct substitution ds to find the limit, we obtain an indefinite form called the indefinite difference, right, which is infinity minus infinity. After successfully using the hospital's rule one time, um, we obtain the limit, which is infinity. The answer is not a numerical value. So what we did here was we took this. Let's see, we're working with g of x on 8. Correct. Okay, so g of x. So we're taking this and we're basically getting antiderivative of this guy here, which where if we convert this to 1 over x to the -1, then we don't get the indefinite form that we were looking. I think we ended up there with yeah, the indefinite difference, as I said. So if we like if we just plug in infinity here and infinity here, it's just infinity infinity, and then we plug that in over, then we end up getting infinity over infinity, I believe. Let me go to my notes here. And maybe the sign may be different there. So let's see, 8. So it's an infinity over negative infinity. Okay, so then once we get that, then we can use the hospital's rule to differentiate the top and bottom separately. Then when we do this, we evaluate out. This is the top only, bottom only, not the quotient rule. So once we cancel out, then we have something here that's natural log of x minus 1 that we can differentiate. I mean, yeah. So anyway, so yeah, that's what we did there. So we just only needed to use it one time to get to this natural log of x minus 1, which we were then able to substitute in here, and we end up with our non what did you call it, a non-valued number, non-numerical value. Okay, so that's how I got infinity there for that guy. So as we can see, it approaches. Let's see, it approaches infinity as x y approaches infinity as x approaches infinity. So we're looking at a graph that just takes off essentially forever. So we move on to number 14. Let's go back up. Sorry, 14. After all the work, the integration by substitution, we finally get the answer for the original integral. Okay, so let's see, we check our answer by giving the derivative. Sorry, because they're opposite operations, so they undo each other. And yeah, this substitution takes care of the chain rule because we can't differentiate sine x squared at this point, with the knowledge that we have so far, at least, as far as I know. So we have to do something to simplify this guy here. This I don't remember what it's called. Anyways, yeah, we got to substitute for that guy so we can get a more basic form that we can integrate, um, and then sub it back in, basically kind of like we did with the chain rule in the first place, where we're just deriving the first part of the term, but then adding the second part of the term in. So like how we are doing here with this integral, we're doing the same thing but opposite direction. So we're just basically say this is the differential of sine u. Then we're just taking the differential of sine like regular and then pretending u is there, and then we're subbing back in the complicated value back in here, and then taking another differential of that complicated value in the chain. So that's how we're undoing it here. We're doing the same thing. We're taking this value out, replacing it something simpler, and moving it back in. We just seem to skip that step kind of when we do the differentiation because it's just a unsaid deal. So that should cover this part here. If you want to know how I got to this ultimate answer here, for differentiating, I mean, we're integrating this guy here, then we're sine give us a negative cosine, and then we apply the 1/2, so we'll have negative cosine u plus c plus our constant value, and then we're going to substitute for u back in, we're going to back substitute the x squared, so then we're going to have a negative 1/2 cosine x squared plus c, and then I just rewrote it because I don't like to write the negatives out front, as c minus 1/2 cosine x squared. Okay, number 19. Oops, get away here. Number 19 for part 1. The resulting integral. Okay, so this I wasn't 100% sure here what you were looking for. I knew you kind of wanted this sine x plus c here. So because we had two spaces, I wrote this out as its own separate because you were just kind of asking about figuring this section out here, in my understanding, by just listing this and not the original uv minus on the front here. So as we got this guy here, minus cosine, so that turned that into a plus here. So as we derive this, we're going to get, see, sine. Deriving sine will get us a positive cosine, so we can go backwards and get us a positive sine plus our constant. So this here is a basic form integral, which is much easier to deal with than x cosine x. which I believe is what we had earlier. Um, so yeah, it's basic. It's a basic one. It's easy for us to solve. The exact verbiage here, I wasn't 100% sure of, but the idea, I was looking for two words that express the idea of what we were doing, which was making it more easily solvable by getting it into a basic form instead of trying to deal with this complicated integral that we might not have the tools to evaluate yet on its own. So that's how I got this portion of the answer for the integral portion of the uv minus integral of uv du, and ended up with that. And then if we go back and we add in the uv portion of this, then we'll add it in 20. And like again, I just mixed up the terms so that I didn't have to write a negative out front. That's what we got there in 20. So okay, 19. So let's move on to part 2, number 1. Part 2, number 1. Okay, so these ones are cool. I like these physics ones. It's interesting to me to see this math and actually get used. So, if we're looking here in theory of relativity, the mass of a particle velocity v is its mass in motion equal to its mass at rest over the square root of 1 minus velocity squared over the speed of sound, or speed of light squared, excuse me. So when we're looking at this, since we're evaluating v as this velocity approaches basically the value of its denominator, um, it's going to become 1 because essentially when it reaches the value of c squared, since this is also squared, it's going to be 1. So when they become equal, when they reach their, which would I guess would be their limit, then they're going to be 1. They're going to subtract from this 1, and we're going to have a radicand of 0, which is going to, the solution will be 0, which gives us a undefined fraction here, making the velocity reaching the speed of light impossible because we're going to be undefined there. So, which is why the left-hand limit is necessary, because uh, if we go beyond c with the value of v, then we're going to end up with a higher value in this fraction than the 1 here, which gives us a negative radicand, and then we start going into imaginary numbers, which again is imaginary. Uh, so that's why the left-hand limit is needed, because this v value cannot actually reach c squared, or cannot actually reach c, because then we get into theoretical instead of physical. So that's what I've written out here. I kind of did them as if v approaches c exactly from both sides necessarily, then I show here that we do have the undefined, that we do have the negative imaginary number here. So the only way that this actually gives us a real world value is by doing it from the left hand limit, um, which is interesting to me because I always hear that you cannot approach. Everything's always listed as 99% of the speed of light when you're talking about travel. It's never like, why can't you travel actual speed of light? And it's nice to see in a mathematical formula here that this is why. Um, so So right here, so yeah, like I said, it's necessary because then we get into basically the imaginary numbers or undefined numbers, um, and we need to remain in the in the real world for this guy. So okay, I think that covers it for number 1. Let's move into number 2, another cool one. Um, so we're looking here. We got our parameters. We got our length at motion to the relative to the observer, which is important. Um, the original length of the object at rest. Uh, and we have the same, basically, it looks like this is a transformation of this other formula here. We're basically just using this denominator here to help us evaluate the length of the object, which is pretty cool. And so a same principle applies here. Although when this does equal 0, we can technically get a 0 here, and it's not undefined, but multiplying the original length at rest times 0 basically means it has no mass. We get 0. So it's telling us that as velocity approaches the speed of light, our object would basically have a 0 length and it would disappear as far as the observer was concerned, um, which is I assume isn't a possibility. So that's why we also need a left-hand limit here, because once this velocity reaches the speed of light here, then the object essentially to the observer disappears, which again is probably an impossibility as far as I know. Um, if not, we just need invisibility cloaks that just go really fast. Anyways, uh, so that's the left-hand limit needed here. I worked it out to where if v was any larger than c coming from the right side, then again we get um, from part A the same calculations. We get a negative number here, which is going to give us an imaginary number. As I'm saying here, if we let v equal beyond the speed of light, 1.1, if we let v equal just below the speed of light, 0.9 the speed of light, then we can actually get a real answer here. Um, and and if I bring it even closer, if I let it be 0.99, then we get, we see that we're approaching 0. We're starting it at about half, close to half here, and then we're down to like 1500ths here of its original size as it approaches closer. So if we do exactly here, like I said, we get 0. It disappears from the perspective of the observer. So that's why the left hand is necessary here, because we can't have an object just disappear, or even, I suppose, if it goes past 0, if velocity exceeds the speed of light, then you're getting possibly a negative length to the object, and again, I don't believe that's possible. Although I was reading that if something's approaching the speed of light, that it actually bends the light, and you can actually see it flips the object, and you actually see the object upside down, where you can see the reverse side of it. Which I don't know if that has anything to do with it. But anyways, that's beyond the scope of the test. I'm just going off on a tangent here. But this one was interesting to me because um, logically, I would think that as something moves by you faster, you're going to see a longer blur of the object instead of like contemplating it getting shorter. That was my original guess, was that you would see that the blur would elongate the object, but it's cool to see here that the math proves the opposite. So, well, that's it for part 1. Okay, so I drift up and part 2 of item 1 was number 2. So we'll go through number 2 here actually for the stretch. So we're evaluating the position of an object moving in a straight line, um, following this path here of this function. So part A, we are doing the average velocity, which we learned early on, is just the slope of a certain interval. So when we take those and we do the difference of those by plugging the values into our function here, we end up with these values here, which are just different points, like I said, just intervals. So over the interval between 1 and 2, we're going to be 0. If we look at our graph here, you can kind of see that. So between 1 and 2, if we draw a line between 1 and 2, we're essentially just right there on the x-axis. So the slope there would be 0. So um, with these intervals themselves alone, we get our average velocities. So when we take our average velocities we obtain in part A, and then we want to estimate our instantaneous velocity. What we're doing is we're taking one of those intervals on either side of our target t value, and we're going to average those two slopes to find essentially our instantaneous velocity at t equals 1. So I did that by using this 1 to 2 interval here, which we found was 0, and then also finding one between 0 and 1 on the other side. That way I got it an interval equal size on either side. And it's simpler than dealing with decimals here. So when I do that, I got -1 from between. Did I get -1? Think I got -2. I did. So I got -2 here, and then divided that by the. So I got the difference in values and the difference in t's. So t1 minus t0 over the value of t1 minus the value of t0 gave me a -2, which gives me. So I got to divide by the number of intervals, which was 2. So then we end up with a -1 meter per second slope at t equals 1. So if we do it using derivatives, we're taking the derivative of this function. We're taking 2t minus 3t plus 0, and then we're subbing in 1 through direct substitution, and we end up with the same answer. So, okay, so analyze the velocity of the object. Complete sentence to say when the object is stopped. The object is moving to left or right. So, if we're looking again at our graph, we're looking at this f of x here. I'm sorry, s of t here, which is our position. And we're looking at the particle moving in a negative direction here to the left until it stops right here at our minimum. So it stops and reverses direction and then starts continuing in a positive direction. So the object from 0 time, because remember this is negative time, it doesn't exist, disregard all of this. So from this 0 to this point here, this minimum here, it's moving to the left. From this point on, because it's continues on infinity. So as this continues on, it's moving to the right. So left, stop, turn around to the right. Okay, part C. So that was C and D. So E, we're analyzing the acceleration of the object. So what we're doing here is we had found the velocity function by taking this derivative here when we were asked to do so in C. So we take that velocity derivative, and we'll take another derivative of that to find our acceleration function. And so where we had 2t minus 3, we now have 2 minus 0. So, and we get rid of our t here because it would be 2. It's a solid 2, and so it's just a constant accelerational value. So we're just a straight line, y equals 2. So that's what I got here. Y equals 2 from basically, I said negative infinity to infinity because, yeah, it does continue on basically forever. However, it maybe should have said 0 to infinity since we are talking about time here. So I will concede that. Let's see, graph the position, velocity, and acceleration functions, which we've seen down below. So while I'm here, we're going to look at this, whether it's speeding up and slowing down. So we got our position function, which is our nice curve here. We got our velocity function, which is in red here, which is negative to coincide with this slope, negative up until this minimum here, which coincides with it crossing into a positive slope. And we can see that that's linear, so it's going at a constant, the velocity function is at a constant slope, so it makes sense that our acceleration is a constant. So y equals 2, straight across here. So when we evaluate whether the object is speeding up or slowing down, for it to speed up, both velocity and both velocity and acceleration need to be the same sign, SIGN, as you said. So as we can see here, acceleration is positive through its entire interval existence, whatever. So acceleration is positive constantly. So where we see the velocity here is in the negative quadrant, they're opposite signs. And so the object is slowing down from 0 until this minimum here where it stops. And then once it hits here, then our positive acceleration aligns with the positive velocity, telling us that from this point on, 1.5, both acceleration and velocity are positive, meaning that this particle is speeding up. And will be doing so to infinity and beyond. So anyways, that's that part. Let's see. I think we have G. I think we got more here. So draft it, speeding up, slowing down. That was G. Displacement. Okay, so displacement and total distance. We'll cover those at the same time as well. So displacement is how far away from its original starting point. I don't know if we can necessarily call that origin to avoid confusion with this guy here, but so the particle starts here at 2, and we see over this interval of 3 seconds that we've been asked to find how far away from its original position has this particle moved. And we can see that it started at 2, it went left, stopped here, and then went back. It turned around and went back right. And if we look at 3 here, it's ended up at exactly the same spot as it started. It started at 2. So essentially, its displacement is 0 because it started here, left, and then came back. So it's not out of place at all. It's exactly where it started. As far as total distance traveled, it did travel down 2, then down another quarter, and then up another quarter, then up 2. So if we look at it analytically like that, just simply, then it's 4.5. We got 2.25, 0.25, 2. So we got 5 there. I mean, 4.5 there. Sorry. So we can tell that, and then we can also do it with the equations. So, which I wrote down in here. So it's displacement. We're looking at basically 0 to 3, 0, and then this turns into 0 as well. So we can do it mathematically and visually. Same here. We're putting in our value because it's changing directions. To see it, we need absolute value of it, and we need to know when it changed directions. So that's why we're putting in t equals 3/2 here, 1.5, and then we're splitting the integral up into basically it's 2 separate intervals, one positive, one negative, and we need the absolute value of those to cover the distance traveled. So when we do that, we end up with the same thing that we figured out visually. So then the last portion of that would be the difference between displacement and total distance traveled. And I think I went over that. So displacement is how far away from its original starting position is the object, and total distance traveled is regardless of where it is now, how far has it traveled, how much distance has it covered, as I said, regardless of its current position and how close that is to where it started. So, I mean, if it went around and you got a particle that traveled around the Earth 500 times and stopped in the same spot, your displacement would be 0, but your total distance traveled, of course, would be 500 times the 20,000 miles or so it is around the Earth. So, anyhow, that should cover all those. And thanks again. Part 2 actually of the video. Yep. So that's that. I'll see you in the next validation. Thanks.